Alright, for this problem, we have a beam, doesn't have any loads applied, but we have our applied loads over here. And it's asking us to find the influence lines for this support reaction at D, and it's a roller, so it'll just be a vertical reaction. And it wants us, by finding the influence lines at D, to find the maximum reaction at D based off of these live loads. So first we're going to create our influence lines, and then we'll apply our loads. The dead load, which is that 1.5, will be the whole span of the beam. The live load, because we want the maximum, it's not like a whole picture view, which is generally what we want to use influence lines for, because we want the maximum reaction. We want to just apply this live load at points where our influence lines are positive. So, and then the point load, which is that 25 kips, will be applied at the highest IL, the highest positive value that we get for our internal, or for our influence line. And there's two ways of solving a problem like this, and there's the quantitative and the qualitative method. Why isn't this selecting? There we go. The quantitative method is very, very thorough, and especially for a reaction, pretty unnecessary. I'm not going to walk through how to do it, but I will just say it can take a lot longer. So we are going to just look at the qualitative method, and I do recommend understanding both kind of approaches to creating influence lines, and then in the future trying as much as possible to only use the qualitative, and then based off of what we have, kind of using like triangles or geometry to solve for any values at any other points that we might, changed up. But yeah, for this, we're just going to use the qualitative method, which is just so much easier. So I really see no reason not to. So we'll just create a line. Actually, let's make that, I hate it not being black. Doesn't even matter, we'll just keep this messy. So this is our influence line, and at point D right here, we'll see that if we were going to put, the idea is that if we were going to put a point load right on top of D, 100% of this point load is going to go sorry, to the support at D. So we show that by putting, let's say if this is our D, this is the end of the beam, we'll put an arrow going straight up, and this will just be the value of 1, stating that this is like a multiplier, that 100% of a load placed right here goes to D. These are just influence lines for the reaction at D. Alright, so we have imposed our positive unit displacement, and if we were looking at rotation, we're not, because it's a roller, we would kind of be thinking about applying a unitless moment there. And next we kind of want to sketch the deflected shapes, but like thinking about how aspects of our member like B, or this pin at A, or this moment release at C, how that's going to affect our shape, or what the deflected shape. And the cool thing is once we have an idea of our deflected shape and kind of have those lines figured out, we pretty much, that, I mean, we've essentially, that's the whole qualitative method in a nutshell, is the deflected shape, yeah, the deflected shape of our member and what we can picture as happening is our influence lines. If that makes sense, sorry. So let me do this in practice. So from here to here, I would see it as no deflection, but this moment shear can cause an up, and this can cause an up. But because this is we're just looking at D, first what we're going to do is just look at the support reactions, and we know that if we put a point load at B or if we put a point load at A, that 100% of a point load at B is going to go to being supported by B, or same thing at A. This is all going to go just here. So for D, if a point load is at B or a point load is at A, that means that my influence lines at these points are also 0. So that's essentially what we're looking at. We're looking at if I put a point load here, if I put a point load here, if I put a point load here, and how it goes just moving across this entire beam. Yeah, finals week and I'm sick. Moving all the way across. All right, so at A, we will see it'll be 0. And at B, if we follow this down, it'll also be at 0. And here, let's do a different color. So I like orange. All right. So because this is all for determinate, our influence lines between points every influence line will be a straight line. So we need to think, because this is a straight line, how this makes sense of what is happening. And I recommend kind of starting from a point that makes the most sense and kind of keeping in mind that right here, this moment release either has it going down like this, or it has it going up, like this. And that's a little off, but, where this is going and then connecting back down. So we can have that kind of up or down happening on both sides. But for between A and B, since this is 0 and this is 0, and we need them to connect, and we can only have a straight line, so it'll just be 0 all the way across. So what this is saying is that any loads applied between A and B, between these 2 points, will cause 0 reaction at D. And this line right here is showing that if we put a reaction right at D, what do we get? We get 100% of that load going to D. All right, so if we're going to go this all the way down, so this is our next difference, and we need this to connect to this point and this to connect over here. So we'll have a straight line here, and then this just goes up, and it's just that easy. That is literally our influence line for D. Now the next thing we want to do is apply our loads and multiply them by the values that we get, that we have. Oops, that was not what I meant to do. I want to copy it, not cut it. So we can just have it, apply our point loads on the beam. Alright, so if you remember, I said dead load has to go all the way, our entire span, no ifs, ands, or buts. That's what a dead load is. So you can see that as going, obviously from here to here, this whole area isn't doing anything. And then, so this will be W sub dl is equal to 1.5 kips per linear foot. And then our live load, we're just going to apply it where we have a positive reaction, because it's a live load, it moves, so therefore we can choose, we have a little bit more flexibility with it, and adding it over here does nothing for us. But yeah, neither does adding the dead load over here, but we need to show that. Just good engineering. And then our point load, like I said, is going to go at this maximum value, whatever the highest point is. Because again, we want the maximum reaction at D. Sorry, 25 kips. And just like normal, this is dy, this is dy. That's just the only reaction we have at D. We want to know what this would equal based on this loading and this information that we have. So we use this area. Get the area, which is going to be equal to 1/2, and that's 30 feet. So 30 of a height with 1. So we get the area is equal to 15. And we're just going to use that for the distributed loads. So that's how their effect at D changes. So let's get to our purple. To find the reaction at D, we need to add all this up. So this will equal, got 25, that's technically being times by 1, plus 2.5 being times by 15, plus 1.5 being times at 15, which will equal 25 plus 2.5 times 15 plus 1.5 times 15 is equal to 85. Oh, don't forget your units. I mean, a teacher would tell you to keep your units on all of your calculations, but who's got time for that?